Okay. Good afternoon. I first thanks IEW for giving me this opportunity to present our work, and obviously Engineers India Limited, my company, to giving the opportunity to come over here and present before this August gathering. So before I start the presentation, I want to give some background, like how we come across this. Like as you all are aware, Engineers India Limited is a leading consultancy in the oil and gas sector, and we do develop technologies in the area of energy efficient technologies. I mean, like you may be knowing about the divided wall column technology, desalter technology, and many more, either alone or in collaboration. So that is one part, and other than that, we do go for the refineries, do energy efficiency improvement studies. So that is another area that we cater. So in that process, what came across is like, okay, the logical way of development. I mean, in the when you do any technology development, you try to go for the process to process heat recovery. So I am talking only about the thermal energy part. So process to process heat recovery. Some more energy is left, then you go for either steam generation. Some more energy left, then you go for maybe DM water heating to go for your deaerator or something like that. So same things for makeup water heaters in a GTHRSG after the steam generation. So, but still in our recent energy audit, like we have done for 15 refineries of India, that is I can say the one of the biggest project in the energy efficiency, maybe across the globe, I can say. So what we have seen, like as everyone is talking about, like maybe in the previous sessions also, even one of the speaker mentioned about the green financing or various technologies that are under development. The thing is like we should focus on the energy efficiency first and technologies that can able to help in achieving that. So with that background, I want to start my presentation. Myself Srivardhan from EIL. So India and the world is marching towards an ambition of net zero. Various companies are having various targets. Do EIL to have that? So a true balance between the GHG generation and consumption, that's the net zero is all about. And in the design of the process, as I mentioned, attempt is generally made to recover as much of heat is possible. But still you have options like which is called as the low level heat, which is generally lost to the atmosphere, and there are various technologies for sure, but there are more alternatives coming up because all the existing technologies are not either energy efficient or not feasible in terms of financials. So the quality of the low level heat which is lost sometimes is a substantial amount. So if we able to recover it, it is a kind of a double benefit. The reason behind to throw away that energy, that low level heat, because maybe the process requirement is at a low temperature, so you need to cool it. So you are additionally consuming energy like in your air coolers or cooling water. So again you are creating a mammoth system to just kill that energy. So if you are developing technologies to recover that energy, then it's a kind of a double benefit. And tapping this low level heat also calls for additional capex obviously, but helps in energy input into the cooling facility. So higher the flow rate and temperature the heat source, the greater is the possibility. So so that there comes integration, like maybe I have multiple low level heat sources, maybe I will just connect them and maybe I can recover it at one place. And the low level heat recovery thus helps in reduction of energy costs and lower emissions, that is what we are talking about, and sustainable future. So low level heat recovery and sources, there could be multiple in any refinery. Like if I talk, there could be product rundowns and overhead condensers and flue gas. Like you can't stay away from them, like that energy is to be lost. So the only option we can see, like when I am talking about energy efficiency improvement, is to recover them. Okay. So what are all the various feasibility? So that all depends upon the states of the process fluid, whether it is a sensible heat or whether it is condensate vapors. and obviously the location of that source and the users and the quantum of usable heat and impact of implementation, like it could be based on the site conditions, or maybe it may not be feasible to recover at all. And yeah, so coming to my topic is Kalina cycle. Most of you must be knowing about it. So when you Google about Kalina cycle, there is a hell lot of information. So I try to simplify it because there are multiple configurations. In my next slides I will also tell about it. So this is very much similar to a Rankine cycle, which we all know. The steam turbine is a steam Rankine cycle, and similar technology is the organic Rankine cycle, where if I want to show, okay, so suppose this is the where I can able to recover energy, evaporator, and it will go what are the vapors that are formed, that goes to a turbine and then it gets condensed, and this condenser liquid then again pumped back into the evaporator. This will close the cycle, and in the turbine would be the generator. Either I can have a generator or I can directly use it in a mechanical system. So this is a simple cycle, and the working fluid inside determines whether it is a steam Rankine cycle or the organic Rankine cycle or the Kalina cycle. Okay, Kalina cycle by the way is developed by Alexander Kalina, and there are multiple patents on it, and this is a thermodynamic process where the heat is transferred to a fluid, obviously at a constant pressure, but the difference between the Rankine cycle and Kalina cycle is here we have two working fluids. That's the beauty of this cycle, and yeah, and the process is very much similar to the Rankine cycle, and there are more working Kalina cycle across the globe. It's not a theoretical study, but it is already already commissioned and running safely. And as I told, there are multiple configurations, and one configuration I am showing here, an optimum Kalina cycle configuration, where for example if I want, for example if I want to, if I have some low level LP steam excess or any other higher steam which can be used for superheating, the superheater, I can add another superheater over here, and for example there is a recuperator here. Like what happens is, suppose in the evaporator not entire amount of the working fluid evaporates. So part of it is in a vapor form, another part is in the liquid form. So what happens is the liquid goes back and it has to come along with this pump at that temperature, so it has to go to the condenser or getting cooled. So what happens is this energy available with this liquid part tries to heat the liquid that is coming from the pump. So this is the recuperator, additional energy recovery here. So that's how the efficiency is further optimized. So many similar recuperators are there, either on the or on the turbine exhaust. So multiple techniques are there. So as I was telling, there are host of optimum Kalina cycle designs. Around 50 patents or even more than that in the literature, and most of them are from the parent company itself. So they all differ between the way the configuration is designed, and there could be multiple turbines, multiple separators, multiple exchangers, multiple heat exchangers. These all depend upon the various heat resources available inside the process plant, whether it is a cement plant, steel plant, refinery. So based on the process, this technology is being adopted and new patents are being filed. So, what are the features? Like till now I was talking about Kalina cycle, but it has a host of features. So any single component working fluid have the pinch or approach point limitations and are at a constant boiling point and cannot cool the gases to the low temperature. So Kalina cycle have an advantage over there, and the boiling point of working fluid occurs over a range of temperature because it is a mixture. and by virtue of varying boiling point and two component working fluid is able to match or run parallel to the gas source or the cooling temperature line while recovering energy. I can show it in an image so that it may be very clear. And that similarly condensation also, and the condenser pressure can be matched into the two component fluid cycle, and thermophysical properties of the mixture can also be matched based on your requirement. Like for example, most notified Kalina cycle designs are with 70% ammonia and 30% water, such kind of combination. So those kind of modifications can also be taken up. And expansion in the turbine can give a saturated vapor in case of the two fluid system, whereas in normal turbines it may be having the wetness. So the protection of the blades in the few stages, in the last few stages, is also not needed. And due to the higher pressure of vapor and low specific volume, the size of the system is very less compared to other thermodynamic cycle. And this is the literature information. Conventional equipment like steam turbines and HRSGs can also be used in Kalina cycle and has been tested across extensively. And as I was mentioning, you can see clearly here, like for example, this is a typical Rankine cycle where this is the single component cycle, the evaporation line and the condensation line. So the hot source over the top and the cooling water on the bottom. But in the Kalina cycle, because of this two fluid system, multi-component cycle, so there will be parallel. So these kind of pinch point kind of issues are not actually present in Kalina cycle. That is where it gains major advantage. And I am just taking you through a single case study. We have done multiple case studies. What all I will explain in the next slides though. So I took one design data of one particular site, so in India. So cooling water supply and return temperatures are very common, like delta being the condenser exchanges and typical header loss, but it will vary from the process to process and pump efficiency. And we try to model it also. So LNRTL was the model that being used, and various other models also checked for authenticity. And even the different databases like WATAM, WATAM, etc. are used for these ammonia water mixtures. So yeah, the database is huge. So what are the points that we have to look while designing this system? Like the temperature and the pressure of the working fluid has to be maintained at the inlet to be in a liquid form. So initially when we are modeling, obviously the model won't run, because you see that the condenser outlet, if you try to reduce the pressure to extract more energy, so obviously you won't be able to run your pump. So exhaust pressure of the turbine has to be maintained in single phase, and ammonia water fraction based on the heat source availability can be matched. And the highest pressure in the system, it all depends upon the turbine and the cooling water system that is available. So just to have a peek into the numbers, this is one of the case that is carried out based on the temperature of the heat source available and the cooling water temperature. For a typical number like 39 megawatt of the heat source that was available at 170 degrees, we could get up to roughly 3 to 4 megawatt of power, and overall thermal efficiency is only to the tune of, I can say only, because I don't say this is also a robust technology, but yes, it is one of the technologies for recovering low level heat, because I could see numbers of around 12% of the overall thermal efficiency in particular simple cases. But it will go, as I told, with other modification I will be showing in the next slides. And 40% of the liquid portion coming from the separator is at high pressure. Please note this point, which will be helpful in the next slide. And availability of excess LP steam can be utilized. And the major components of the costing here are the turbines, generator, and pumps. Like, okay, whenever you go talk to any vendor about organic Rankine cycle or any other cycle, the biggest question comes is like most of the parts are imported. Like with Atmanirbhar Bharat in mind, Like if we can able to indigenize most of these components, so obviously the cost figures will be very attractive. So as I was mentioning, what are all the other modifications? Few innovations we at EL we have looked at. Like one about is the pressure recovery device. Like you, as I was, sorry, uh, as I was mentioning, so this is a pressure recovery device. Okay, yeah, this is a pressure recovery device. As I was mentioning, the liquid from the recuperator is again at a high pressure, but it has to be killed to meet with the low pressure saturated vapor. But one technique what we developed, what we have seen is like a pressure recovery device, but there is a Chinese patent in it, but we have tested it. So here the energy in the liquid side can be used to take out the low pressure saturated vapor, so that on the exhaust of the turbine we can reduce the pressure further. So that improves the efficiency further. Another thing is about the cooling water. Like if I am able to have any chilled water source by any means, so that can also be able to improve the efficiency. Another approach is the multi-turbine approach. As I was mentioning, the liquid on the after the recuperator is at high pressure. So if I flash it further, so I have more steam, so that more working fluid in vapor form, which can be used to another turbine. So it again improves. Like by doing many of these changes, the system will be large, increases the capex, but yes, efficiency goes up. And multiple working fluids, like because I said this is a mixture of components like ammonia, water also. So multiple organic fluids, alcohols were tested, but yes, we also ended up saying that the ammonia water mixture is the best, which is reported in the literature. And to conclude what I have said till now, the low level heat recovery helps to improve the efficiency of the operating plants, and it is a sustainable solution. As though these technologies show you higher capex, yes, there should be green investments happening, even in the research part, even in the implementation, commercialization parts. And the Kalina cycle is one of the technologies in the low level heat recovery, and the overall thermal efficiency with not many modifications is at 9.5 to 11.5%. And as I mentioned, with some modifications, this efficiency can be further improved. And the consumption of cooling water side also advantage has to be taken, as I was mentioning. And the pressure available in the liquid portion can be recovered. So one technology I have shown here, there are multiple other technologies also. So some of them are already patented, and these technologies provide leverage to design techniques to enhance efficiency for capturing the energy available. And the Kalina cycle offers advantage compared to other cycles other Rankine cycles because of its cost benefits, because of low transport of fluid requirements. That is the biggest USP of this technology. And yeah, so I can say that this is one of the green technologies that has to be considered. And my final thoughts for net zero, because everyone is talking about net zero, let us conserve energy, let us maintain the hydrological balance and pollution reduction, and thank you once again.
Thank you, Srivardhan, for that